Very good morning, students. Today's session we are going to discuss bond parameters and polarity of bonds. So in this video, the following topics we are going to discuss: bond length, bond order, bond angle, bond enthalpy, resonance, polarity of bonds, partial covalent character in ionic bonds, and Fajan's rules. The first one, bond length. The distance between the nuclei of two covalently bonded atoms is called bond length. The distance between the nuclei of two covalently bonded atoms is called bond length. Now, what is bond order? Bond order is nothing but the number of bonds formed between the two bonded atoms in a molecule is called bond order. For example, the hydrogen molecule, between two hydrogen, how many bonds are present? Only one bond. Between two oxygen, two bonds. Between two nitrogen, three bonds. Between hydrogen and cyanide, three bonds. In formaldehyde, number of bonds between carbon and oxygen, two bonds. Carbon and hydrogen in methane, one bond. In ethane, between two carbon, two bonds. So bond order is nothing but number of bond between two bonded atoms in a molecule. Let us discuss bond angle. Covalent bonds are directional in nature and are oriented in specific direction in space. This directional nature creates a fixed angle between two covalent bonds in a molecule, and this angle is termed as bond angle. It is usually expressed in degrees. The bond angle can be determined by spectroscopic methods, and it can give some idea about the shape of the molecules. For example, methane bond angle 109 degree 28 minutes, in ammonia 107 degree 18 minutes, in water 104 degree 35 minutes. Now, bond enthalpy. Bond enthalpy means the minimum energy required to break 1 mole of a particular bond in molecule in their gaseous state. The minimum amount of energy required to break 1 mole of a particular bond in a molecule in their gaseous state. The unit kilojoule per mole, right? For example, in water there are two OH bonds present, and the energy needed to break them are not same in water. So the bond is breaking between hydrogen and OH group. So how much energy is required? 502 kilojoule per mole. The bond breaking between oxygen and hydrogen, the energy 427 kilojoule per mole. So the average bond enthalpy of OH bond in water 502 plus 427 divided by 2 equal to 464.5 kilojoule per mole. Now let me see resonance. Let us consider the Lewis structure of carbonate ion CO3 2-. So three types of structure we can give it, that is called resonance. The fourth one somewhat different, somewhat as different from the first three, right? The only differ in the position of bonding of lone pair of electron. The first three, when we compare the first three, they only differ in the position of bonding and lone pair of electron, right? Such structure are called as resonance structure. So these three are called as resonance structure. They only differ in the position of bonding and lone pair of electron. So just you go through the structure, we can find the difference. C double bond O, it is in left side, but here the second one it is up, the third one it is right side. They differ in the position of bonding and lone pair of electron. Such structures are called as a resonance structure or canonical structure. This phenomenon is called resonance. So what is resonance? We can understand it. Now the first three structure is the difference between the fourth one. The difference in energy between the structure 1 or 2 or 3 with the structure 4, resonance hybrid. This structure, the fourth structure is resonance hybrid. That is called resonance energy. The first three structure is compared with the fourth one. So we can find the difference in energy level. That is called resonance energy. So here, what is energy? What is energy and what is resonance energy? We can find it. So next one, polarity of bonds. Polarity of bonds. Let us consider the covalent bond between hydrogen and fluorine in hydrogen fluoride. Just if we take a hydrogen fluoride molecule, the electronegativity of hydrogen and fluorine on Pauling scale are 2.1 and 4. Hydrogen electronegativity value 2.1 and fluorine electronegativity value 4 respectively. It means that fluorine attract the shared pair of electron approximately twice as much as the hydrogen, because hydrogen 2.1 and fluorine 4, so approximately twice as much as the hydrogen, which leads to partial negative charge on the fluorine. So in the HF molecule, fluorine has a partially negative and hydrogen has partially positive. The HF bond is said to be polar covalent bond. Here, a very small equal and opposite charges are separated by a small difference. 91 pm, picometer, is referred to as the dipole, right? That is called polarity of bond. So in a molecule, which one carries a negative, which one carries a positive, we have to find it regarding electronegativity, right? Now, what is dipole moment? The polarity of a bond, covalent bond, can be measured in terms of a dipole moment, which is defined as nu equal to q into 2d, where nu is the dipole moment, q is a charge, and 2d is the distance between the two charges, plus q and minus q. The dipole moment is a vector, and the direction of the dipole moment vector points from the negative charge to positive charge. Now, the unit for dipole moment is coulomb meter. It is expressed by N d by unit d. So 1 d by equal to 3.336 multiple with 10 to the power minus 30 coulomb meter, means d by d. Some examples we can see. The molecules have some dipole moment values. Diatomic molecule such as hydrogen, oxygen, fluorine have zero dipole moment. These are called non-polar molecules. Zero dipole moment means non-polar molecule. Certain molecule such as hydrofluoric acid, hydrochloric acid, carbon monoxide, nitrogen oxide have non-zero dipole moment, are called polar molecules. So zero dipole moment means non-polar. The valued dipole moment non-zero means polar molecules. Molecules having polar bonds will not necessarily have a dipole moment. For example, a linear form of carbon dioxide has zero dipole moment, even though it has two polar bonds. In carbon dioxide, the dipole moment of two polar bonds, carbon monoxide, are equal in CO, or equal in magnitude. It's a carbon dioxide, right? C double bond O, double bond O. So, but have opposite direction. Hence, the net dipole moment of the CO2 is zero, right? The oxygen, it pulls a shared pair of electron both sides, so the dipole moment value 0. In case of water, the net dipole moment is the vector sum of mu1 plus mu2. We can see the dipole moment of water in water is found to be 1.85 d coulomb meter, right? So why? Because here oxygen has partially negative and both hydrogen partially positive. The oxygen more electronegative, it pulls the electron towards itself. That's why inverted V-shaped structure is occurring. So not only that, if the electronegativity difference between A and B atom in a molecule is equal to 1.7, then the bond AB has 50% ionic character. So the electronegativity difference 1.7 means 50% ionic character will occur. If it is greater than 1.7 means more than 50% ionic character will occur. If it is lesser than 1.7 means the bond AB has less than 50% ionic character, right? So next we see the partial covalent character in ionic bonds. Here, what is polarization, what is polarizing ability and polarizability, we can find it. There is an electrostatic force. So what is polarization? There is an electrostatic force, attractive force between the cation and anion. So in electronegative compound or electrovalent compound, ionic compound, we can find it. The positively charged cation attract the valence electron of the anion while repelling the nucleus. This causes a distortion in the electron cloud of the anion, and its electron density drifts towards the cation, which results in some sharing of valence electron between these ions. Thus, the partial covalent character is developed between them. This is known as polarization. This is known as polarization. The partial covalent character in ionic compounds or electrovalent compounds can be explained on the basis of a phenomenon called polarization. In ionic compound, we can find the covalent character. That's the meaning, right? Now, polarizability and polarizing ability. What is the meaning? We will see. The ability of a cation to polarize an anion is called its polarizing ability. I repeat it. The ability of a cation to polarize an anion is called its polarizing ability. And the tendency of an anion to get polarized is called its polarizability. And the tendency of an anion to get polarized is called its polarizability. So regarding polarization, polarizing ability and the polarizability, we can find Fajan's rule. Here we can find the covalent character in ionic bond. Smaller cation and a larger anion are going to make a bond. So it is ionic bond, but they give the covalent character, right? To show greater covalent character, both the cation and anion should have high charge on them. Higher the positive charge on the cation, greater will be the attraction on the electron cloud of the anion. Similarly, higher the magnitude of negative charge on the anion, greater is its polarizability. Hence, the increase in charge on the cation or in anion increases the covalent character. So cation has higher positive charge, so attraction power is maximum, right? The higher magnitude of a negative charge on the anion, greater is its polarizability. So anyway, increase in charge on the cation or in anion increase the covalent character. So let us consider the ionic compound aluminum chloride, magnesium chloride and sodium chloride. 3 salts we have to take. Here negative ions are same, but positive ions, sodium, magnesium, aluminum, that's all, size of the cations are different, right? So here Na plus is less than magnesium 2 plus, magnesium 2 plus less than Al 3 plus. The covalent character also follows the same order because the charge of the cation increases, right? So aluminum 3 plus has greater covalent character than magnesium 2 plus. Magnesium 2 plus is greater than sodium plus. The smaller cation and larger anion show greater covalent character due to greater extent of polarization. For example, here lithium is very smaller cation compared with sodium. Here lithium chloride is more covalent than the sodium chloride. The size of lithium plus is smaller than the Na plus. Hence, the polarizing power of lithium is more. Lithium iodide is more covalent than the lithium chloride. Here, lithium chloride and lithium iodide is compared. So, both metal positive cations are same, negative ions are different, The iodide is compared with the chlorine. Iodide size is very large. So smaller cation, larger anion means they give greater covalent character. So lithium iodide is more covalent than the lithium chloride, as the size of iodide is larger than the chloride. Hence iodide will be more polarized than chloride by the cation of lithium plus. So third point, cations having NS2 NP6 ND10 configuration. So greater polarizing power than the cation with the NS2 NP6 configuration. So which type of metal cation we can take this kind of electronic configuration? NS2 NP6 ND10. So good example, copper chloride. So copper atomic number 29, right? So when we write the electronic configuration, we can get it until D10. Here copper chloride is more covalent than the sodium chloride. Compared to Na plus 1.13 Armstrong unit, copper plus 0.6 Armstrong unit is very small and have 3s2, 3p6, 3d10 electronic configuration. So electronic configuration of copper plus 3d10 and electronic configuration of Na plus 1s2, 2s2, 2p6. So cations copper plus having greater polarizing power than the cation of sodium. Thank you.